Hey everyone, and welcome to this explainer. Look, if you've been working in mechanical engineering or product design for any amount of time, you've almost certainly specified ABS on a drawing. It's everywhere, right? But I want to challenge a pretty common misconception right out of the gate. ABS is not just some generic, tough plastic. Not even close. It's actually a highly nuanced terpopolymer that blends three distinct monomers together at the molecular level. And to get that flawless Class A surface finish and hold those incredibly tight tolerances we all want, it requires some seriously precise process control. So today we are putting together the ultimate technical brief on ABS injection molding.
Okay, let's dive right into our roadmap for today. First, we'll cover the ABS materials properties profile, then injection molding process parameters, followed by comparing ABS alternatives, troubleshooting common molding defects, and finally, engineering and industry applications.
Section 1. ABS Material Properties Profile. The chemical foundation and baseline specs of a crucial engineering thermoplastic.
So ABS actually stands for Acrylonitrile Butadiene Styrene. It's what we call a terrapolymer. That just means it achieves its incredible performance by blending three entirely different monomers together. First, the acrylonitrile provides chemical resistance and rigidity. Then the styrene delivers the processability and that beautiful high-gloss surface. But the real magic here, that's the butadiene rubber. This rubbery polybutadiene phase is basically dispersed throughout the rigid matrix, and it allows the material to dissipate and absorb impact energy without brittle fracture. That right there is the absolute secret behind its legendary toughness.
Now, take a look at these baseline mechanicals. Notice the flexural modulus sitting between 2.1 and 2.5 gigapascals, alongside a tensile strength of 40 to 50 megapascals. For us mechanical engineers, this tells us that ABS is incredibly stiff. But thanks to that butadiene rubber we just talked about, it is not brittle. It offers fantastic structural rigidity while maintaining a highly predictable dimensional stability.
And speaking of dimensional stability, if there is literally one single number you memorize today, make it this one, 0.4 to 0.7%. That is the post-molding linear shrinkage rate of standard ABS. This incredibly low, highly predictable shrinkage number is exactly why ABS is the absolute go-to thermoplastic when you need to hold exceptionally tight, precise tolerances in high-volume production.
However, we really need to correct a massive engineering misconception right here. ABS is not a high-heat material. Its continuous use temperature maxes out between 80 and 95 degrees Celsius. Its glass transition temperature is right around 105 degrees Celsius. If your part is going to sit in an environment hotter than that, it is going to soften and deform under load. Simple as that. So if you need higher thermal limits, you absolutely need to be looking at a PC/ABS alloy or just pure polycarbonate.
Right, moving on to Section 2, Injection Molding Process Parameters, executing the perfect part from resin to cooling.
So here is the rigorous 6-step life cycle of an ABS pellet. I really want you to frame this in your mind not just as a rough guideline, but as a strict, non-negotiable manufacturing protocol. Deviating from these exact steps is exactly how you introduce processing pitfalls and completely ruin otherwise perfectly good tooling runs.
Step 1 is arguably the most critical. Drying is non-negotiable. See, ABS is highly hygroscopic, which means it literally pulls moisture straight out of the atmosphere. You have to dry it at 80 to 85 degrees Celsius for 2 to 4 hours in a closed-loop dehumidifying hopper. Your target? Get that moisture content below 0.1%. If you fail to properly dry the resin, that trapped water is going to boil during injection. This instantly induces those ugly silver splay marks, ruins your surface finish, and completely destroys the material's impact strength.
Once the resin is perfectly dry, the melt enters the mold. Now, your injection pressure needs to sit firmly in the 70 to 130 megapascal range. Your part's specific geometry is what dictates exactly where you land on that spectrum. If you're designing really thin-walled, complex housings, you're going to need to push toward that 130 megapascal upper limit just to ensure complete cavity fill. But if you've got thick structural components, you want to drop to the lower end. That way you pack the mold fully while minimizing the residual internal stresses that inevitably lead to warpage down the line.
Okay, this next part is absolutely crucial, getting the trapped air out of the mold cavity as that plastic rushes in. Your mold needs vent depths of 0.025 to 0.05 millimeters, placed strategically right at the last fill areas. And guys, this isn't just about avoiding cosmetic burn marks or short shots. If your venting is inadequate, the compressed gas superheats the ABS. This degrades that crucial butadiene rubber and actually generates toxic acrolein and styrene vapors. Proper venting is quite literally a safety requirement, not just a quality one.
To make sure this flow behaves perfectly, we have to follow some strict Design for Manufacturing or DFM guidelines. First, use a minimum radii of 0.5 times the wall thickness at your transitions to avoid stress concentrations. Keep a nice uniform nominal wall between 2 and 3 millimeters, and make sure to apply 1 to 2 degrees of draft per side for a clean ejection. Finally, always position your gate at the thickest section of the part so the molten plastic can properly pack and flow outward. Okay, let's see how ABS actually stacks up against the competition.
Section 3. Comparing ABS alternatives. Benchmarking ABS against polypropylene and polycarbonate.
This benchmark data beautifully positions ABS in the broader market. Look at polycarbonate, that's your high-tier option, right? It handles heat up to 130 degrees Celsius and has massive impact resistance, but it is expensive and much harder to process. Then you have polypropylene, which is your low-cost commodity option. But ABS, it sits perfectly right in the middle, offering high impact resistance and fantastic shrinkage predictability at a very reasonable cost point.
Now, it's all about trade-offs, right? While polypropylene certainly boasts superior chemical resistance against harsh solvents, ABS wins the contest entirely when it comes to isotropic strength. It delivers a pristine Class A surface finish, and it completely locks in that ultra-predictable 0.4 to 0.7% shrinkage rate for precise assemblies.
Section 4. Troubleshooting common molding defects. Mapping defect diagnostics to immediate corrective actions.
When you're troubleshooting on the factory floor, you always want to look for direct cause and effect. If you see sink marks where a thick wall has caved in, that means your outer skin cooled while the inner core shrunk. You immediately need to increase packing pressure and time. If you see parts warping right as they eject, your cooling is non-uniform, so you need to balance your water channels to stop that differential shrinkage. And if you see silver streaks or splay, just like we talked about earlier, someone skipped the drying protocol.
And hey, here is a highly actionable tip for everyone chasing that flawless, high-gloss Class A surface finish without wanting to pay for secondary painting. If your part is looking dull, raise your mold temperature. Pushing the mold temperature up to between 60 and 70 degrees Celsius allows that styrene monomer we talked about to pack smoothly against the polished cavity steel right before it freezes. It's a game changer.
Finally, Section 5. Engineering and industry applications, where ABS dominates the market.
Standard ABS is great, for sure, but specialty additives are what truly unlock massive global sectors for this material. In automotive, heat-stabilized grades are used constantly for interior trims and dashboard bezels. In consumer electronics, you literally cannot manufacture a power supply housing without using a halogenated or phosphorus-based flame-retardant ABS grade that hits that strict UL 94V0 safety rating. And over in the medical sector, OEM suppliers rely heavily on FDA 21 CFR compliant ABS for non-implantable diagnostic equipment enclosures, which are processed in clean rooms with full material traceability.
So, we're going to leave you with this final engineering challenge. ABS is an incredibly capable, highly predictable turopolymer when processed correctly, but it absolutely has very definitive thermal and chemical sealings. Knowing its precise limits, does standard ABS truly meet the exact specifications of your next project, or is it maybe time to start engineering with advanced polycarbonate alloys? Take this data, apply it to your next design review, and specify with confidence. Thanks so much for joining us on this explainer.